Hello students, welcome back. Let's begin section 2, Modular Arithmetic. This topic is relatively minor, at least for the time being, so let's try to get it over with as quickly as possible. First, modular operation, and this one is really no big deal, but it does serve as a kind of stepping stone toward the next one, so let's talk about it as briefly as possible. Let's begin with the division algorithm. Remember this? And that? Well, in the division algorithm, please recognize that the quotient and remainder, which I'm highlighting right now, are uniquely determined given A and B, the dividend and divisor, which are arbitrary. So that blah blah blah, the second line. Now what does that mean? That means we can define a function, a double variable function, which determines Q from A and B, and also another function which defines R from A and B. Q and R are uniquely determined, so those kind of functions are uniquely well defined, and those kind of double variable functions are called algebraic operations. In this particular case, they're called the div operator and the mod operator, respectively. Did I say operator? Sorry about that. Div operation and mod operation. Forget about operator stuff. Sorry about that. I just misspoke. Div operation, or integer division operation, or the quotient operation, and the modular operation, or the remainder operation. Those are double variable functions with some algebraic structure. As for details of those operations, or binary operations to be a little bit more precise, well, I'll just dump it over to abstract algebra. Over there, it's an important topic, so whoever's teaching abstract algebra will do a good job covering that aspect. For now, we'll just define div operation and mod operation, quotient and remainder, and we can express those using the greatest integer function or floor function like these. If you're not familiar with floor function or the greatest integer function, well, for now you can forget about those. Those will become relatively important in the second half of the course, and at that moment we're going to talk a little bit more about the floor function or the greatest integer function. For now, just div and mod. Okay, those are the definitions. How about some example problems? Okay, here's one. 18 mod 7. Also, I can consider 18 div 7 as well, because mod operation is a little bit more important. In this notebook, I just wrote mod operation, but I can also consider div operations as well. Okay, what are those? If you want to try, stop the playback and try. What do you get? Well, time's up. 18 divided by 7, here's the division algorithm. 2 times 7 is 14, and that's the closest. So the quotient 2 and the remainder 4. Those are mod operation and div operation, respectively. Mod is a little bit more important. How about this one? Time's up. Negative 43 is negative 44 plus 1. Remember, we are dividing by a positive divisor, so the remainder must be non-negative. So that's 1. And this is negative 4. Again, div operation is a little bit less important, so let's de-emphasize those in gray. And the third problem, I don't know whether this thing is worthy of our class time, but here we go. You can do these kind of problems too, with minimal use of calculation tool. Okay, so much for div and mod operations, but neither is very, very important as a matter of fact. I talked about those as the kind of stepping stone towards what is important. Here we go, modular equivalence or congruence. This will become very, very important in a couple of weeks, maybe about 3, but that can wait. For now, just consider those as a preview of what's to come, with some minimal details that I would prefer you to remember. Because using these, I can explain a lot of things in a lot more straightforward and easier to understand fashion in the next 2 or 3 lessons. That's why I'm introducing this a little bit ahead of schedule. Okay, here we go. Here's the definition. Let m be a positive integer. We say a and b are congruent modulo m or equivalent modulo m if m divides the difference a minus b. You can write like this. A minus b is some integer times m. Yeah, that's the definition. And you can use this kind of notation, using this triple bar to represent the equivalence or congruence, and then express modulo m like this with parentheses, or like this using subscript. Either way you can do it. Both notations are widely accepted, so you have to know both. So I'm going to mix those up so that everybody is exposed to both of them. Even more so, when there's no danger of confusion, I'll just use this without specifying m. You know, if you have a single problem with a lot of congruences, but they're all modulo 9, for example, then I'll just use this. If they are modulo 9 and modulo 17 and modulo 12 mixing up, in that case, each time I'll have to specify like this or that. That's the definition of the congruence. Now, how are they related to the modular operation? Aspect number 1 is like this. A pair of integers a and b are congruent, modulo m, if they share the same remainder. And the remainder computation is modular operation, so that's how they're related. Here we go. You can write a and b with division algorithm, q1m plus r, and q2m plus r. They share the same remainder, and that's the same as a and b being congruent, both congruent to r. How do you prove it? Well, flip this r to the other side. What happens? Subtract, and then subtract, and that disappears, and then what do you have? A minus r is divisible by m. That's precisely what we have over here. That's the very definition of the congruence. You can do the same thing here as well. So that's the proof. It's that simple. Let's go back to where it was. Now, in a special case, when r is 0, then it's the same as a some integer times m, so m divides a, and that's the same as a is congruent to 0 modulo m. So sometimes it's better to use this, sometimes it's more convenient to use this. You have to know both. And this is a primary reason that I'm talking about this congruence a little bit ahead of schedule. Okay, another aspect. The mod operation and modular equivalence are related kind of like this. R is a mod m, and a is congruent to r modulo m are the same thing if r is between 0 and m. Now, what if we drop this? Then these two are not equivalent anymore. R can be still too big, maybe. In general, we have this. That's the general case. Now, in a special case, when we have this condition, r is between 0 and m, then these two are the same. Okay, so much for modular equivalences. Do we have an example problems? But oh, come on, this is stupid. I'll just leave it to you. Just divide by 6, divide by 8, divide by 10, divide by 12, and check those remainders. Next topic, modular arithmetic. Here it comes, the title of this section. That's going to be the main role. Okay, here we go. If a and b are congruent and c and d are congruent, then the congruence preserves the addition and also the multiplication. In short, as far as the addition and multiplication are concerned, this congruence works just like the equality. If you add the same thing to both left-hand side and right-hand side, the equality is preserved. If you add the same thing to both left-hand side and right-hand side, the equality is preserved. That's the same thing you're seeing here, as far as we have congruence modulo m, and m is not changing. The proofs, well, proofs are not that important for the time being at least, but it's not too difficult, so let's talk about those. So a and b equivalent, so the difference a minus b is divisible by m, so some integer I times m. Same here, c minus c is some integer j times m, and we have to have two different integers I and j because whenever we have an existential quantifiers, make sure you get two different characters. M should stay the same because m is given. So from these two, we have to prove that the difference between these two, left-hand side minus right-hand side, is divisible by m, some integer times m. It's easy. All you have to do is to switch the order of these two, like this. A minus b plus c minus d, so we have im plus jm, factor m out, voila, we have integer times m, so we have the congruence. That was easy. How about multiplication? A bit tricky here, but it's not too bad either. Same thing here, and then we want the left-hand side minus right-hand side is divisible by m. What kind of manipulation do we do here? Well, we do something ingenious, which is very typical in analysis. We subtract and add by something clever. But if I add and subtract by same thing, you're just adding 0, so no change took place. But this changed into first 2 and second 2 are kind of like this. First two terms, which I just highlighted in blue, have c in common, so factor those out. And the second have b in common, so factor b out. So factoring those out, c and b respectively, we have a minus b and c minus d respectively, and those are both divisible by m. So factor m out, voila, we have an integer times m. That completes the proof. Tricky and kind of ingenious, but remember this trick. It's very typical in analysis. Anyway, we went through these and we proved those, but far more important for you is how to use those. Basically, you can add and multiply freely. Want to see an example? I hope we have enough time for that. Let's see. 3 to the 5th power minus 4 to the 7th power times 7 to the 8th power modulo 9. Okay, all right. Let's do that computation. What is 3 to the 5th power? 3 squared is 9, so that's 0. 3 to the 5th power is 3 squared times something, so that's 0. Oh, that was simple. This entire thing is 0. And we can do this kind of congruence computation for all kind of multiplication easily. And then we are going to subtract. That's because we went through all those and proved all those in 2.5. Now let's go over to 4 to the 7th power. Turns out 4 squared is 16, which is 18 minus 2, so negative 2. So 4th power is negative 2 squared, so back to 4. So 4 to the 7th power is 4th power times 3rd power, but 4th power is back down to 4. So 4 to the 4th power, that's back down to 4. All right, now how about 7 to the 8th power? Okay, 7 is 9 minus 2, so negative 2. So 7 squared is negative 2 squared, so it's 4. So 7 squared to the 4th power, so 4 to the 4th power, and we went through that already, that's 4. Here's a conclusion. 0 minus 4 times 4, negative 16, which is negative of negative 2, so it's positive 2. This kind of computation tells you that we're going to do all kind of addition and multiplication, subtraction, all those freely with any kind of repetition. I'm going to leave the second problem to you. All you have to remember is mod 7 operation because there are 7 days in a week.